Good morning, good afternoon, good evening, everyone who's joining us. I can see already have over 70 people joining. That's exciting. Today, we're going to talk about how you can graduate from OpenAI to open source. Originally, it was 11 best practices, but this team is so sharp. It's now 12 best practices for distilling smaller models from large models like GPT, or really any large model. So we'll cover a lot of best practices. Real quick, as you're logging in here, we have a few polling questions I'll start to push out just to learn about the audience. You can also see sort of what your peers are up to, what they're doing with LLMs, and get a sense of some of the challenges and successes they're having. So we'll share those polling questions. They're in the sidebar. Feel free to participate if you'd like while you wait. And with that, we'll kind of get moving here. All right, so a few web logistics. My name is Michael. I lead marketing at Predibase. I'll be your moderator for today's session. A few just minor logistics. The chat window on to the right there on your screen is open. You can say hello. We're dialing in from San Francisco, New York. Always love to see where all of our friends joining us are dialing in from, so feel free to say hi. Today's session will be muted, so your means of communicating with our presenters will be via chat. We will answer the questions. We'll have a live Q&A at the end of the session. And we also have some of our technical folks online who can dive in and answer questions you may have in the chat. So please make use of chat. Ask us questions around the topics. We're here to help educate you and help you learn. The session will be recorded, so you can access it afterwards and share it with your peers. And then additionally, if you're interested in trying out Predibase, we have an awesome 2-week free trial. You can fine-tune and serve an unlimited number of open source models on the platform for 2 weeks. You can try it out. And also, we have 2 actually open source projects, which we'll talk about briefly today, Ludwig and Lorax. One is for fine tuning and sort of building custom models, the other for serving them. You should check those out as well. Today, we're joined by 2 great presenters. We got Justin and Yael from the Predibase team. Justin is a founding staff engineer here at Predibase with deep experience in language models and language applications while working at Google and also doing research projects. Yael as well, who's joining us, has a lot of experience both at Predibase, like Justin, building our LLM capabilities, but also training and fine-tuning language models, and also building language-based applications at Apple. So you have 2 awesome experts to walk you through today's content. And with that, I'm going to hand it over to Justin. And a reminder, Justin, you're still muted.
Yes, hello. Can everyone hear me? Is everyone able to sound good? Okay. Thanks, Michael, for the nice, very warm introduction. Yeah, very excited to run this webinar with Yael, my esteemed colleague here today. To kind of get things kicked off, wanted to share this, synthesized quote from a lot of conversations we've had. So, almost every organization we've worked with, and probably I imagine most people joining us today, you've built at least one novel internal application using LLMs. One larger company we spoke to told us they built 70 prototypes in 1 week. So at the same time, most people we talk to are saying that they want to move off these, OpenAI LLMs in the near future. And why is that? So turns out that OpenAI is actually really great. So it's really easy to use, no modeling knowledge required, just an English language prompt, and you're using AI. The performance, in particular with GPT-4, feels really good, and that's really inspiring. It was for me anyway. But OpenAI is great until it's not. Before we get too far ahead of ourselves, being victims of our own success, we should do a little reality check of what it's actually going to be like to try to use OpenAI in a real production scaled application. So 1, we don't own the model, we don't own the IP, and we never will. 2, it's expensive at scale. These per token costs definitely will rack up. And then 3, GPT, in my experience, it can be slow, it can be rate limited, and sometimes it's just literally unavailable. So we're trying to think about a solution that gives us ownership, but also improves our cost efficiency. And this brings us to this core idea of model distillation of open source models. Open source, because that's kind of what gives us full ownership, and model distillation, because this is actually a technique that's been around for a while, but fundamentally it's something that enables you to replicate larger models in the form of a more manageable, more cost-effective, smaller model, often without a significant or sometimes any loss in performance. So that sounds great, but is it really that easy? And we're going to discuss today, but model distillation, in some scenarios, you can actually be reasonably optimistic that it should work, but it can also be pretty non-trivial to get right. But when it does actually work, it is really amazing. And so that's why today, I think we're really excited to share with you these kind of 12 best practices for model distillation, along with some experimental results on a real use case. So how did we come up with these 12 best practices, and why should you kind of listen to us? So a quick note on our background. Before Predibase, I developed generative language models as part of Google Research. And in the beginning, we were just researching models and doing a lot of TensorFlow coding. But as our team shifted to productionizing these models for real, this is where model efficiency becomes very, very important. And there was probably many months of the year where I was distilling hundreds of language models per day. And as an accumulation of this experience, our team published a paper on distilling all of these language models. Specifically, these are neural machine translation models. And then I think my colleague, Wael, has also published a paper here, also related to NLP, and as part of his work at Stanford. And then at Predibase, we believe that the future is fine-tuned. It's fine-tuned specialized LLMs for your tasks. And Wael and I, we're part of a larger team, but we maintain two relatively popular open source libraries. One of them is Ludwig, which now has over 10,000 stars on GitHub. Very excited about that. And then Lorax, which has only been out for a few weeks, and it's already racked up over 500 commits from 40 contributors. So to sum it all up, we have some experience, and we're also very passionate about this topic. Before we get into it, I want to define some commonly used terminology when we talk about model distillation. So first, large language models. These are the advanced AI models that are trained on vast amounts of text data, like ChatGPT, for example. They seem to have a deep understanding of language, and they can be trained to follow instructions or other tasks involving text. Model distillation, we talked about this already. In academic circles, you might also hear this called imitation learning, because we're trying to get a smaller model to imitate a larger model. The teacher model, so this is the capable larger model that we're aiming to transfer into the smaller model. And then the student model, this is the smaller model that the teacher model is distilled into. So in terms of like model distillation and graduating from OpenAI to open source, this is kind of like a rough picture, and we'll come back to this kind of at the end of the talk as well. But the high-level idea is we want some way to collect data or extract data from this teacher model. We want to use that data to then distill a fine-tuned open source model. And then once we have that distilled good open source model, we can just use that in production, and thereby eliminating our dependence on the original teacher model. So now I'll hand it off to Wael to talk about his experiments with a very concrete case. Wael.
All right, thank you, Justin. Let's do the next slide. Yeah, so the Jigsaw dataset is a collection of online comments. It's a mix of offensive and non-offensive comments. It originally contains fine-grained labels such as toxic, severe toxic, obscene, etc. But for the purposes of this webinar, we collapsed all these columns into one column to obtain a binary classification dataset. The distribution of this dataset is 90% of the labels are non-toxic and 10% are toxic. We're working with this dataset having in mind two goals. The first is to evaluate OpenAI models, namely GPT-4 and GPT 3.5 on this binary classification task. And the second goal is to explore fine-tuned models as an option for distilling these larger closed source models. We see here the performance of GPT-4 and GPT 3.5. Before we did that, we set aside a test set of 400 rows, of which 50% are non-toxic examples and 50% are toxic examples. We see that GPT-4 scores 88.8% on accuracy, whereas GPT 3.5 Turbo scores 85.8% on accuracy. This is expected, as we know that GPT-4 surpasses the previous version on multiple benchmarks. For the second goal, we're interested in investigating the impact of various factors on the performance of these fine-tuned LLMs. And the first axis we wanted to focus on is data, namely on quality and quantity. So we took the original data and subsampled 6 partitions of this data set. The first being an in-distribution, meaning a data set that has the same distribution of 10% toxic, 90% non-toxic. And this in-distribution data set has GPT labels. So these are not the true gold labels from the original data, but they're labels that we used GPT-4 to generate. Second data set is the same as the first, plus 1.1 thousand rows of in-distribution gold labels. So we added another 1,100 rows of gold labels to both increase the size of the data set and improve the quality of the data set. C is the same as B, but we filtered the examples that GPT-4 got wrong. And this simulates us keeping the dataset size the same while improving the quality of the dataset. For D, it's the same as B, but we wanted to change the distribution of the dataset, so we added 1,000 rows of gold toxic labels. So now about a third are toxic examples, and the remaining 2/3 are non-toxic examples. E and F, we're testing the scale of the data, the size of the data and its impact on the quality of the model. So we have in distribution data sets, both GPT labeled. One is 5,000 rows and the second one is 10,000 rows. The second axis we wanted to test is the model variant. We got a lot of questions on which one is better. Is it Llama, is it Mistral, or are they the same? The final axis we wanted to test is the model size. We want to answer the following question of whether a 7 billion model is enough, or do we need a 13 billion model to improve on quality? Next. And these are the results we get. As we see on the graph, GPT-4 already performs well. This is a testament to the power of large language models. However, we see that smaller, fine-tuned open source models outperform GPT-4, although they're fine-tuned on much less data and they're much smaller in size. So we have Llama 2 7 billion performing at 91.2%, Mistral 7 billion performing a little bit better at 92% accuracy, and Llama 13 billion performing at 92.7%. And it seems here that if we fix for the same model variant, for the same data and hyperparameters, we get better performance using Llama 2 13 billion. You go to the next couple slides. Yeah, so open source wins and larger models perform a little better. And just a note, we are evaluating all these models on the same exact test set, same 400 rows, 50% non-toxic and 50% toxic. So that was a cross-model comparison to really compare the model variance and sizes. Let's double-click on Mistral 7 billion instruct as an example, so we can take a look at the differences in model performance across the different data sets. So for the first one, that's an in-distribution GPT labeled data set. It has a performance of 87.2%. The performance from GPT-4 is 88.8%. And this underperforms, and that's expected because the data set is really generated from GPT-4. So there's really a bit of a ceiling in terms of performance on that data set. But once we bump both the size and the quality of the data set, the performance jumps by 2.8 points to 90%. And once we move to C, which takes B and removes the labels that GPT got wrong, while slightly dropping the size of the data set, we jump by 2 more points. So this really shows that data quality is really, really important, and it's paramount to the performance of your model. Next, and if we look at D, that's an experiment where we disturb the distribution of the data. So we have more toxic labeled examples, and this one is a very interesting one because it shows us that we have to be very, very careful when crafting our training set, because it might really impact the results on the test set. If you go to the next couple slides. And the last two ones are E and F. Here we're comparing the scale of the data sets and the impact of the size of the data set. So the corresponding comparison is A. So we compare A, E, and F. And we see that when we move from 1.1 rows of in-distribution GPT labeled data to a data set that's about 5 times its size, the performance jumps by 3 points. But when we move from E to F, doubling the size, the performance doesn't really improve that much. So there are some diminishing returns. So data size is very important, but if there's something to really focus on, it would be the quality of the data set. And that can push the performance really, really far. You're on mute, Justin.
Okay, cool. Yeah, thanks, Weil, for going through some of the experimental results with distilling this Jigsaw model. So now let's jump right into the best practices. So there's 12 of them. That's ambitious, but I think we can get through all of them. And please note that actually part of some of these best practices are code samples and more technical snippets that we're going to go through pretty quickly during the webinar. But you can find them on this Predibase LLM distillation playbook. This is a GitHub repo that we just made public, where it's very minimal, but it's basically just these best practices written out with some sample code, modeling notebooks, and we're planning to add more to turn it into a formal artifact of this webinar. But if you want to get a quick preview and you end up checking out the repo, definitely leave a star. That would be much appreciated. Cool. So let's dive right in. So number 1, best practice. What are the limitations of smaller models? So if you are kind of feeling skeptical about this whole imitation learning thing, you don't need to look any further than this paper from researchers at UC Berkeley. So this paper, titled "The False Promise of Imitating Proprietary LLMs," basically finds that they basically find that for their student models, they're able to mimic these larger models in an impressive way. But then upon closer inspection, they actually do so while falling short on factual correctness. So that's a little bit unfortunate. It's not unlike some students that I've worked with in the past. However, Microsoft's work on Orca basically refutes this, and they show that particularly for these kind of more complicated problems that require more reasoning, if you actually take the time to train the student models on what's effectively a richer data set from the teacher that includes stuff like the step-by-step deductive reasoning, then these students will pick up on that logic as well, on those reasoning skills, and they still are going to be pretty good. We recently published our own blog post showing that you can outperform these proprietary LLMs as well in this JSON generation named entity recognition use case. So we have Jigsaw, we have this, we have the Orca model, but then we also have this paper from Berkeley. So what's going on here is model distillation a thing that works or is it not? So in truth, and I know people don't like this answer, but it depends. When it comes to tasks that require substantial reasoning abilities, generally this is kind of going up into the left quadrant, the top left quadrant. Students are going to be, more likely to be disadvantaged, and they're going to need more assistance to match the teachers. Conversely, for narrow tasks that are more straightforward, a fixed, outputs, then there's actually a really good chance that you'll get a competitive student in no time at all. So anyhow, that's it for number one, getting some understanding of the limitations of these smaller models. Number two, build good logging infrastructure. So let's say that just this Jigsaw data set didn't exist, but I had this sample application that uses ChatGPT on the fly to tell me if a comment is toxic or not. Here's the basic infrastructure for what my app does. In this case, OpenAI will be my model as a service, or MAS, I'm not sure how to pronounce it. Here's what my application Python code kind of looks like using the chat completion API. This probably looks familiar to a lot of you. And so the idea is that I can start to bootstrap my own toxicity classification data set simply by logging my requests and responses. If you haven't already thought about more seriously logging stuff in your application, you really should think about it. Tokens are expensive, and data is the new oil. And so if you just want to go for a lean V0, you can kind of stream your requests and responses to some AWS S3 bucket, like so. I also want to take a moment to acknowledge that in the chat, I think there's some questions about whether this, is a violation of OpenAI's policy. And, to the extent that I think the advice that we're sharing here is more about, model distillation in general, but absolutely, before you, put anything in production, you should definitely check by policies and what you're allowed to do and what you're not allowed to do. Cool. So to make logging, non-blocking on the main thread, you can use a queue and then flush to S3 asynchronously. So this is just like a very lean V0 for getting your logging started. Obviously, if you have an official logging service or a logging service vendor, they should be able to provide these as well. So let's actually imagine that your legal team comes back to you and says, oh, actually, you can't do logging because of PII, or maybe there's other policies that you have to watch out for. So we'll also say that hope is still not lost on model distillation. You can actually try to use your teacher model to invent infinite amounts of training data. So here, hey, can you come up with all of my training data for my use case? And then you can kind of just repeat that ad infinitum. So last week, I learned about this cool tool called DataStand that's designed actually specifically for this purpose. You basically provide your task. In this case, it's search queries about flights. And you click AI text generate, and then an LLM, probably ChatGPT, generates some synthetic data for you. However, and this is not to bash on DataStand's demo here, it really does seem like a functional product. But their demo actually highlights the biggest challenge with synthetic data, which is even though you're able to get this LLM to produce an infinite amount of data, the big challenge is to ensure that the examples that it actually comes up with are varied and non-repetitive. So you'll see that all of the synthetically generated examples here are virtually identical, most of them referring to Tokyo, which is probably a very popular place. That said, there are actually ways to get varied and diverse, meaningfully diverse synthetic data. And that can be a viable option in the absence of other data such as logs. But just be aware that synthetic data generation methods are definitely a bespoke thing right now. So specific to your domain, your task, you might have to come up with a specific scheme to kind of get that diversity. But if you're interested in this line of work, I definitely recommend checking out this self-instruct paper, the Microsoft Phi models, and the AlpaCare papers, which are all kind of distilling from GPT-4 or GPT 3.5. So as we wrap up best practice number 2, building good logging infrastructure, I will leave you with this quote that I found really interesting from Microsoft. We speculate that the creation of synthetic data sets will become, in the near future, an important technical skill and essential topic of research in AI. Cool. Number 3, define clear evaluation criteria. So this should already be a very well-known best practice for machine learning, but it's so important that it's worth reiterating. Effective evaluation of distilled models, or really any model, it requires clearly defined criteria that align with your specific application's needs. The choice of evaluation metrics should reflect the nature of the problem and the desired outcomes of your model. There's a growing trend of using LLMs themselves actually to assess model outputs. And this is really interesting because manual evaluation by human raters can be slow and expensive. Just calling it out as kind of a trendy approach, and you might find it compelling, like we did for many actually different use cases, but it really does require some care around biases. And finally, establishing clear test sets that you can track over time and compare to other models and checkpoints is really critical. And ideally, your test sets should be diverse as well, and they have good coverage. All right, best practice number 4, maximize the quality of your teacher model. So here we have a depiction of a student and a teacher. And the student is following the teacher. And we can hopefully understand that in model distillation, you can think of the quality of your teacher's model's outputs as an upper limit for the quality of your distilled student model. I think Wael referred to this, in his experiment where he showed that, the student model it's really hard for the student model to, get ahead of the teacher. So what does this mean? This means that you should invest in maximizing the quality of your teacher's model's performance as much as possible. So how do we do this? Well, first, you want to choose a good teacher. There's a lot of choices out there. And here's kind of like a little graphic to show different specialties and skill sets. GPT-4 is generally a safe choice, though it's possible that there are other teachers that are trained on data that's similar to your task, and therefore they might be a better teacher out of the box. The prompt itself makes a big difference, obviously. So it's worth spending some time to find a good prompt. Something that I like to do is that I start with a super concise, simple prompt. I try making it shorter. I try making it longer. Maybe I include a few shot examples. And then I also like to play around with prompt parameters like max U tokens and temperature, just to get a lay of the land in terms of accuracy. A quick anecdote is that this think step-by-step prompt was widely lauded as a trivial way to get just jumps in quality when you're doing zero-shot inference. However, this actually turned out not to be the case for a toxicity classification teacher. And the theory is that perhaps too much reasoning about whether a comment is toxic or not leads to more false positives. So in summary, for best practice number 4, you want to maximize your teacher model quality by choosing a good teacher and then doing prompt engineering to make sure you choose a good prompt and good prompt parameters. Number 5, maximize the quality of your training data. So if you can continue enhancing the quality of your training data with or without help from more teachers, you absolutely should. And you should do this because bugs and deficiencies in your data will absolutely materialize in your student models. Addressing these deficiencies at the source is better than relying on downstream auxiliary systems. And so from least difficult to most difficult, we have a few suggestions to talk about today. One is just manually fix your bad outputs. This is a labor-intensive process, but it's a simple way to correct for bad examples. Then you can filter out bad data. Just drop bad examples from your data set. This can also be done manually, but sort of one-upping that, oftentimes there's a clever rule you can come up with, maybe some regular expression, maybe some pattern that you can apply it to your entire data set at scale. Ranking your data with auxiliary systems. This is basically like filtering your data automatically, neural network style. So you score all of your data with some other system. This could be another LLM or teacher, but specifically tasked with scoring rather than generating. And then you just drop the bottom, let's say 10% of your examples. This is effective, but it's a little bit rough around the edges. So I would only recommend doing this if you can afford to lose some data. We mentioned earlier that with Microsoft's Orca paper, basically you can also collect this deductive reasoning signal, show your work text from your teachers. And the extra explanation traces they've shown can help students improve their inherent reasoning skills, and that might get missed with answers-only training. And then for some tasks, you can use training or majority voting to effectively create an ensemble of teachers, or the same teacher parameterized in different ways to produce your higher quality outputs. So condensing multiple teachers' knowledge all together onto single labels, and then you have one student that trains on the final, and then maybe some leapfrogging can happen. So that's it for number 5. Hopefully these handful of techniques will give you some ideas for how to maximize the quality of your training data. Number 6, the best data sets are diverse and balanced. So we covered this in best practice number 2 when we talked about bootstrapping a data set. The main challenge with the synthetic data is to make sure that it's non-homogeneous and diverse. However, just because you're using logs and not synthetic data doesn't mean that they're actually any better. We might naturally assume that real traffic brings us a good balanced variety of inputs and outputs, but in practice, this is actually rarely true. You want to make sure that certain power users, for example, like this person who always wants to travel to Tokyo, are not represented in your data set based on your logs. So some techniques that have been proven very handy for myself include debiasing the logs by mutation. So, find these entities or, in these examples, and then explicitly just swap them out for random locations. Then you can, if you have rare cases in your logs, you can actually augment that in your data set by sending them through a paraphrasing or a back translation stack. And then finally, if you just know that there's missing cases that need to be handled, you can just manually add them. So potentially, there's a lot to think about here. I'll say that on specifically balance and diversity of your data sets, it's not essential to address everything up front, but it's useful to kind of anticipate some of these issues that might come up when you actually start doing model evaluation. So, if you've picked a good test set, you should also, be pretty worry-free, because, if you've picked a good test set, these meaningful data biases, they should become apparent when you actually evaluate your model. Okay, so number 7, start simple and start small. The big point here for this best practice is that in your early experimentation, much like starting a new company, you really need to be aggressively optimizing for iteration and feedback velocity over everything else. More complex models are harder to understand, harder to explain, harder to backtrack. And sometimes, it's really cool to use the newest, biggest, nichest, 600 billion parameter model thing. And you should absolutely run that experiment, but just do it after you've run your naive baselines first. Naive baselines, they serve as clear benchmarks to measure the performance of your later, more sophisticated model configurations and experiments. So definitely make sure those are really, really solid, because a metric means nothing if there's nothing meaningful to compare it to. So number 8, how much data? We actually we started with 11 best practices, as Michael mentioned, but we actually decided to make this one number 12, because this is actually one of the most common questions that we get asked, which is, how much data do I actually need to fine tune my model? And again, this is the answer that no one likes, but it really depends. In our experience, you can get pretty meaningful results with a few hundred to tens of thousands of examples, but there's definitely people who have been able to get meaningful results with much fewer, and also people who had to use many more examples as well. But if you are dying to get an answer to this question for your task and data set, one kind of useful thing you can do is to run an ablation study, varying your data set size, and then kind of do some extrapolation. So for example, here we can see that the difference between my 50% of my data and my 100% of my data, it's pretty marginal. So, I can already do some extrapolation that if I were to somehow magically double my data, the improvement will still probably just be a marginal one. All right, number 9, consider how you want to serve your student. So to explain the nuance here, we'll want to do a quick primer on fine-tuning. So in the world of fine-tuning LLMs, you have this kind of dichotomy between traditional fine-tuning and something called parameter-efficient fine-tuning. In normal fine-tuning for large language models, you have your data set, and then you're aiming to update kind of all 7 billion or how many ever of the parameters in each step. This is very expensive from both a memory perspective as well as a checkpoint perspective, because of all of those parameters that you have to kind of track updates for. But then there's this alternative that essentially says, instead of adjusting all of the weights of the model, I'm just going to adjust a very small percentage of the weights and that I've introduced as new weights and fine tune those. And so the result is that we keep the base model the same, and the new sets of weights we call an adapter is very small, usually on the order of 1% or so of the model of the original parameters. So one of the most popular approaches for parameter efficient fine-tuning is something called low rank adaptation, or LoRA. And in this technique, we basically introduce 2 new tensors alongside certain layers of the original model. And each of these tensors is very small, but then when you multiply them out, they basically have the same shape as the original base model tensors. And so you can kind of just add the outputs together when you're computing the final prediction. And this property actually makes it very easy to serve this type of model in production alongside the original model, because all you have to do is load in, all your base weights, and then, compute the outputs on the same input for each of these additional weights, and then sum them up. So how does this look in production when you actually go and deploy it? In a typical model deployment, like a dedicated deployment, you're going to have some, let's say Kubernetes pod. And if you're running on Kubernetes, that's kind of the physical container for the model. And you'll have some, request queue that allows you to accept incoming requests from users. And then you have the pre-trained base model weights, in this light yellow color. And then you have a small number of adapter weights that are loaded alongside. And this is in the blue color here. So as you go and deploy more of these models, you're going to end up, spinning a bunch of dedicated deployments for each model. But you'll kind of see that if you're using the same base models for some of these deployments, that most of the parameters themselves in GPU memory, all in this light yellow color, they're actually exactly the same. So this is kind of one of the key ideas behind Lorax, which we open sourced less than a month ago. And this is the ability to efficiently deploy multiple LLMs into the same machine by sharing the same base weights, loading all of the adapters together, and then maintaining separate request queues for each of the adapters that can be managed intelligently with a separate scheduling system. And with the Predibase API, this would look something like this. You first get the adapted LLM for a base model, and then you proceed to prompt it. The costs of serving parameter-efficient, fine-tuned models on Lorax are ridiculously cheap compared to dedicated deployments. So if that kind of cost efficiency would kind of be a game changer for your application, it would be very smart to start thinking about aiming the bulk of your experiments towards parameter-efficient fine-tuning rather than full fine-tuning. So there's actually a lot of cool stuff happening on the Lorax GitHub repo. Definitely check out Travis's presentation on it from last week, linked in the presentation here as well. The GitHub repo is there. There's a Discord channel that is super, super active if you're interested in contributing. And again, if you want to hit the ground running with a Colab notebook with a side-by-side comparison of kind of the results you might get with full fine-tuning versus parameter-efficient fine-tuning, and you just want to kind of try it out for yourself, the Predibase blog actually has many tutorials now for you to read for fine-tuning Llama or Mistral, and Zephyr is coming up soon. And the other option, of course, is you can sign up for a free trial of the managed platform at predibase.com. Cool. Number 10, we're almost done here. Experiment broadly, one parameter at a time. So some top tips. So you have your teacher set, you have your data set, you started small, you got your naive baselines. Okay, so now it's time where you're actually gonna just kick off like a million experiments. Some tips for this part of the journey. One, it's really important to stay organized with model repositories, like if you're using Predibase or something like spreadsheets. It's great to parallelize your experiments, but try to just change one parameter at a time. This way, if you notice an improvement or you notice a degradation, it's very easy to track what parameter that was that changed. You should expect some toil and some guesswork. Deep learning at the end of the day, fine-tuning is deep learning, and deep learning at the end of the day is a very empirical kind of science. So expect to see some surprising results and trying to do some detective work to figure out, how and why the model did that. And then similar to kind of a previous best practice, you still want to optimize for iteration speed. Progressing from simple to complex, progressing from small to large. There's a ton of bells and whistles in deep learning, and most parameters, they probably don't really matter to the final quality outcome. So just start simple and then progressively add complexity. So there's surprisingly little information out there, or I should say little centralized information out there about the best way to fine-tune your LLM. So, here we've kind of curated a list that, comes from our attempts to actually crystallize our own approach. So starting from kind of the least difficult to the most difficult, pick a good foundation model for your student. There's many different student models that you could start from. So try swapping out a few different foundation models and see what happens to your performance. You can also try different model sizes. I think 7 billion is very, very popular to start with, but it could be worth just to kick off a 70 and a 34 just to see like what kind of impact that makes. Cool. Precision or quantization. So we've seen this be really impactful because using a lower precision allows you to train with larger batch sizes because you can basically fit more examples into memory. And the ding to quality is, either very small or non-existent. And so, and even if there is a ding, it's usually quite minimal compared to the gains you get in speed and size reduction. And there's hyperparameter tuning, obviously. Some of our favorite hyperparameters include rank and alpha for LoRa-based fine-tuning. The learning rate obviously is extremely impactful, and also the number of epochs. Sometimes you just have to train for longer, and then you'll suddenly get a better model. The last thing we'll mention here, kind of like the most advanced stuff, is I'll mention two things. So one is progressive learning. This is also called curriculum learning. And it's a training strategy where, the model is fine-tuned in a series of stages, each with a different kind of training data, typically progressing from your more general, noisier data down to more specific, high quality and in-domain data. And progressive learning kind of mirrors the way that humans learn. You start from broad concepts and you gradually focus on more specific and complex ideas. This is a lot more logistics to manage in your training pipeline. But this is a technique that people have seen a lot of success with. Another very advanced option is RLHF, RLHAIF, or DPO. I've also seen this called preference tuning, where the model undergoes kind of this reinforcement learning regime to align better to human preferences. This was originally popularized by OpenAI, but people have found that it's really costly, and it's definitely like a sort of a last mile optimization sort of thing. So we have yet to speak with a company who has a critical need for this kind of optimization, but it is sort of the most advanced form of experimenting broadly. So that's it for number 10. Hopefully you have lots of ideas for how to run experiments. So number 11, actually looking at the model's mistakes. For generative language tasks, it's not uncommon to have a single automatic metric that transparently tells you if your model is producing good language or bad language. And so we have these loss curves though, perplexity, loss, but besides going down and to the right, these loss curves actually tell you very little. And when I see them, they mean very little to me when I see this kind of line in terms of understanding the actual performance of my LLM, because there's no text. So we should see some text. And so this is a kind of a screenshot of the Predibase platform where we actually show you samples of your outputs during and after training for every checkpoint. And so the idea is that if you're just going by perplexity and loss, that's okay. But really manually reviewing examples of your model's actual outputs brings a lot of value for you in terms of getting a deeper qualitative understanding of your model performance. I recommend doing this often and early, and you'll find that you're going to build a pretty good intuition for how well your LLMs are faring on your task. It is more laborsome, but it's going to be worth it. Okay, this is the last best practice. We made it to number 12. I hope people have been having a blast with these because I'm certainly having fun talking about them. So best practice number 12, actually deploy and monitor your models in production, actually. So a lot of people get to that point where they have a good model and they're like, oh, cool, I'm done. Classic, research engineer type move. But there's actually a lot that you're going to learn when you actually try to use your application, use your model in your application in production. So these test sets that we've talked about, it's really that's basically a controlled environment for evaluation. But the true test of your model's effectiveness is, how it impacts your business. How does it actually perform with your actual users, and how does it, handle real-time inputs? So push for deploying your model in observing its performance in a real world setting. So on deployments, there are some safeguards that you should set up. So one is monitoring inputs. Fine-tuned models, they are more specialized, so they are going to be potentially more sensitive to feature drift. So if your inputs are suddenly changing for some reason, it's good to have a mechanism that will catch that. Monitoring outputs. So LLMs, at the end of the day, they're still black boxes. So you want to have some quality assurance or some confidence, at least, in what you're actually serving to your users. So what I've seen is that LLMs production are often accompanied by kind of rules-based or model-based systems to kind of identify issues with the LLM outputs and potentially trigger fallbacks or kind of notify an on-call person. And so it's kind of like a fail-safe kind of mechanism, fail-safe guardrail kind of mechanism. But just be aware that if you're using sort of another LLM for output monitoring, that could add latency to the overall system. And then also you want to maintain logs. So we talked about the importance of logging, in best practice number 2. But just because you've even after you've deployed your distilled model, you should just continue logging the outputs, inputs and outputs, if you can, because these logs are going to be invaluable for future model refinements, evaluations, or even redistillations. Options for model deployment. So I've listed 3 here. There's probably others. Live experiment and a gradual rollout. So something you can do is you put the student model up for serving, and then you kind of direct a small percentage of traffic to it. You start with 1%, and then you kind of monitor, you want to monitor changes in key application metrics, like latency and user interactions. And if they all look good, there's no impact or maybe positive impact, then you roll out to 10% and then to 50% and then 100%. Dark launching is also an option. You basically continue to use the teacher model in production, but you kind of route a portion of the traffic to a student model in the background. And then, this way you can kind of do that analysis offline, and you can compare instances where the student's model's predictions differ from the teacher's to evaluate, its overall readiness. You're not going to get stuff like impact to latency or impact to user interactions, but on the quality side, this is definitely, a pretty safe option. And then hybrid launch. So, this is particularly maybe more relevant if this teacher just continues to be superior to the student. You can kind of, have both serving at the same time, where maybe the student model can handle these simpler, less resource intensive queries, while, you leave the teacher to address kind of the low confidence queries or the more complex requests. Cool. So I know that was a lot. I feel like I did a lot of talking there, but in summary, we went through all 12 best practices for distilling smaller models from GPT. This is kind of a collage of all of them. They're also on the LLM distillation playbook that we have on our GitHub. But yeah, I'm going to hand it back over to Wael to tell us where we go from here.
Thank you, Justin, for the amazing tips. So before we talk about the path forward, I want to reiterate what we observe to be the state of LLMs today from conversations we have with customers and prospects. Some companies have built prototypes with OpenAI models, and some of these prototypes have made it into production. Yet, people are looking around to find solutions for some concerns that they have. People are concerned about cost at scale, because although the pricing of these model as a service solutions is friendly for building prototypes, they're very expensive at scale. People are also concerned about quality, because although these models are very powerful, they remain generalists, and they're not best in class in very specific tasks, and they have performance limitations especially when we get to niche tasks or tasks that are not using English as the language. People are also concerned about control over their models. Customers would like control over the models, and some need guarantees around latency and throughput. And finally, privacy. When using proprietary models, you're sending your data to a third party. Some organizations cannot afford to do that, and others who can still afford to do that, they prefer not to. So the path forward we propose is that proprietary models are a great starting point for adding AI capabilities to your organization, but there are better alternatives, and open source LLMs are that alternative because they're more performant, they're cheaper, and they're faster. Next slide. So what does graduating from OpenAI to open source look like? If you have a system or workflow in production that's based on a closed source model, that's already a great start. You have AI in your organization. Not a lot of people have that. What you can do from now is to start capturing your interactions with these APIs when allowed. So make sure to check the terms and conditions of the model as a service platform, and you can collect this data and use it to fine-tune open source large language models. And then when you fine-tune your model and evaluate it, you're happy with your first evaluation, the model will probably be on par with this teacher model. You can deploy it and you can keep iterating on the data using the tips that Justin mentioned, and you can retrain your models. When you improve the quality of the data, the quality of the predictions of the models will improve, as we have seen with our own experiments. And then you'll be in a situation where you have a model that's better than the closed source model, and you'll be able to serve it 50 times cheaper on Predibase. So how can you get started with Predibase? Predibase is the developer's platform for productionizing open source AI. In Predibase, we've built cross-cloud efficient, best-in-class infrastructure so you can train and deploy any open source LLM. You can bring your data with you, whatever it is, wherever it is, whether it's in Snowflake, and S3, or even a local CSV. We provide pay-as-you-go options for LLMs that are 50 times cheaper than OpenAI, as well as enterprise options for training and serving your models privately in your VPC. So join our free trial and try out Predibase today. With that, I'm happy to open it up to questions.
Thank you to our presenters for that awesome session. Double click on what Wild said. Try the platform for 2 weeks. It's free, no credit card, anything. You can fine tune and serve as many open source LLMs as you want. We support a lot of cool ones like the Llama series, Mistral, and Zephyr, and some others. So there's a lot of Q&A. I know people have been actively answering them in the sidebar, but let's jump into some of them. So just to start out early on, there's some questions on like, one, just how do Mistral and Llama do when they're not fine tuned in your opinion?
How do they do on the task we tried?
Yeah, perhaps for this task, more broadly speaking.
Oh, yeah. For this task, I tried Llama and Mistral. The output was not formatted correctly. So there's, of course, right after the LLM does its generation, there's a processing step that we do on the text, and the LLMs would answer to the prompt. The prompt would be, given this comment, classify it as toxic or non-toxic, and they would answer as, I'm not able to classify, or something like that, right? So fine-tuning really, really helps with not only the specific style you want to generate in, but the actual task.
Great. So a lot of questions about fine-tuning. Just want to ask specifically, like, is it worth fine-tuning models that are already instruction or chat-tuned versus like fine-tuning a foundation model? What are your thoughts on sort of fine-tuning those models?
We tried different variants. We tried Llama 7 billion, Mistral, Instruct. One experiment I've tried was the Llama Chat. We've seen that Llama Chat and Llama, there are no major differences. Mistral is slightly better, but I wouldn't really, it's not better by a really big margin. I would really focus on picking an architecture. Start small. A 7 billion model or even smaller is enough. Really focus on the quality of the data. And yeah, the quality of the data is what's going to get you the highest improvements, rather than trying different models.
Yeah, just jumping in here with one quick additional comment. In fine-tuning, you are really updating the weights of the model. So there's kind of less to fear in terms of, picking picking a base model that is like truly as close as possible to your task. If you have good data, as Wael said, the model is going to eventually conform to, optimize the loss on that. Yeah.
Great. I know we're close on time, but I'm going to get a few more questions in because there's a lot about like data specifically as relates to fine tuning. So actually one was, related to like, if you're, in the examples you gave where you're training on the labeled data from GPT or GPT generated data, can the model actually outperform GPT? Is that possible? I think you guys spoke to this a little bit, maybe reiterate, like, is that possible to outperform?
Yeah.
Oh, good. Go ahead, Justin.
Oh yeah, it's absolutely possible. We talked about different ways that you can maximize your data quality offline. Simple things like just dropping the bad examples, filtering out bad examples, or just adding new human labeled data. These are all, ways that you could see your student model become better than what the teacher could do out of the box.
Got it. And is like having a larger batch size always good for fine tuning? That came up as a fine tuning specific question.
The thing with the batch size is that fine-tuning large language models is slow because the models are really large, right? So if the batch size is already small, you're going to be updating the model one batch of size 1 at a time, right? And then that's going to be very, very slow. The model will take hours, maybe even half a day or a whole day, depending on the data set size. So the reason why I think it's important to get the maximum batch size that you can fit in the GPU and use that, and then tune the other parameters, is that so you can speed up the training and the iteration process. So you can iterate on other parameters, learning rate, gradient accumulation. You can iterate on your data, and that'll be more beneficial.
Got it. A lot of questions around the sort of data reasoning for fine tuning. So one, in the example we gave, some might consider like a simple problem binary classification. Maybe something more complex in a real world scenario. Like, how do you think about the amount of data required to fine tune successfully?
Yeah, fine tuning a model for binary classification is certainly not the hardest task. There are open-ended generation questions, open-ended generation problems that are much more difficult. I think for this task, you can get away with 1,000 examples, right? We tried 1,000 examples and the model performed pretty well. You can probably get away with less than that. For other problems such as code generation or any text generation or anything like that, it will probably depend on whether you need structured text or not, the size of the output you're trying to generate, the complexity of the formatting, for example. So it's going to depend, I think. But yeah, for the easier tasks, less than 5,000, and then there's probably a bracket of medium tasks that are up to 10,000, and later maybe there's like more.
Great. All right, this will be our last question to both of you. Someone asked, how do you think about like the quality of the data? How do you distinguish good from bad? Maybe it's a philosophical question. I'm sure you have some real world experience.
I mean, yeah, it's kind of up to, I would hope that you as the proprietor of your use case, you can do that distinguishing. I think if a human can't do it, then there's little hope that an LLM could do it. Yeah, certainly, I think Weil was saying like sometimes LLMs will just say, "Oh, I don't know how to respond to that." That's probably an answer that you would example that you would want to drop from your data set, because you don't want to have that student mimic that kind of uncertainty. Yeah.
Well, anything to add on quality data?
Yeah, I mean, what Justin said is spot on. I think, yeah, people know their tasks, and they're the best judges of their data.
All right. Hey, guys, this was an awesome session. Lots of questions. We try to get to all of them either live or in the chat. If we didn't, feel free to reach out to our speakers afterwards, via LinkedIn. And of course, this recording we made available to everyone. Thank you again for joining us today. Really enjoyed the interactivity with everyone. So have a great rest of your day wherever you are around the world.